Hello, hello, hello. Welcome back. It is Wednesday, the 29th of April, and today we're going to be going through waves, standing waves, and optics. That was the one. I was like, wait a minute, what am I doing again? So hope you all are having a good day. I know who's really having a good day are the people doing the IB because they have just finished their physics. IB happens very, very early, so they just sat their second paper today, and now they're looking forward to just sort of getting on with the rest of it, finishing off with the math. They're done in like 3 weeks, and then they get the whole summer ahead. So they're chilling. They're sitting pretty. The rest of us doing A levels, we have a long road ahead. 6 weeks or so, 6 weeks and a little bit. But yeah, you can really feel it now, can't you? Like a lot of the learning has already been done, and now it's just like refining it, doing all the papers, getting all the technique done. Like you can feel the energy of exam season, or at least you're gonna get it from me. So today's gonna be a bit of waves, a bit of optics. I'm thinking, again, I'm gonna run this the way I would do it. Like if you had an exam tomorrow on this topic, what are like the really important things I would want you to hold on to? I'm gonna assume that you've got the prerequisites down. Like you guys know what amplitude is, you know what wavelength is, you know what frequency is, you know what time period is. I'm going to say you know how to use an oscilloscope, but if I'm wrong about that, drop it in the chat. As always, I'm very chat-led, so if you have a particular question, I'm happy to go where you guys want to lead me. But the main thing I want to go through is like standing waves, which is new, superposition of waves and how it sets up the standing waves. So just lots of things on stationary waves. And then go into the optics stuff. So refraction with a little bit of extra on top of what you did at GCSE, and then going into interference, double slit experiment, diffraction gratings, things like that, especially those derivations, which people really hate. So yeah, as I'm going, feel free to drop things in the chat if it's not clear, and let's just get into it. So I'm going to drop you guys as usual. You guys are going over here on the second screen. If I can make that work, there we go. And let's get into it. So the first thing to understand, so I'm assuming you guys understand the wave equation, V equals F lambda. I'm assuming you understand amplitude, frequency, wavelength, time period, all those sorts of things. Let's first talk about the new thing that happens at A level, that's superposition of waves. Now that definition is that when you have two waves meeting at a point, the total displacement is the sum of the individual displacements at that point. So if we have a point in space where there's one wave at its sort of maximum amplitude at that point, and another wave also at their maximum amplitude at that point, the sum of these displacements, or rather the individual displacements, will be added together. So this displacement here plus this displacement here will give you the total displacement, which is sort of twice as big. So that's what happens when two waves meet at a point. You get the first displacement, you get the second displacement, you add them together, and that gives you the new displacement at that point. Now, if the two waves are arriving, this is called in phase because they are at the same point in their cycle. But if they arrive in out of phase, which means they are at opposite points of their cycle, they will destructively interfere. So for instance, if I have this wave doing this at the same time as this wave is doing this, then at this point in time, this guy's at maximum, this guy's at minimum, and the vector displacement here would be this much. So let's call that x up, and let's call this y down. The total amplitude there would be x minus y. So that's the idea behind superposition. You find out the individual displacements, you add them together, and that tells you the displacement after they combine. So, and a lot of the very interesting things about A-level waves are what to do with that. So this is standing waves, this is interference, this is diffraction gratings. And those are the three cases I really want to emphasize today. So first, let's talk about standing waves. So how are standing waves set up? That's a really important one. That comes up a lot, that explanation. So standing waves are set up. First of all, you need the sources to be coherent, which means they have the same frequency, constant path difference. Well, that's more of a double slit thing. For standing waves, what you say is you have one progressive wave traveling down. It then reflects back. Because I have two waves moving through each other with the same frequency, you may ask your question, sir. Because I have two waves moving through each other with the same frequency, that is what allows a standing wave to be set up. Because the two waves moving through each other will superpose, just like we saw there. And there will be regions where they are superposing constructively, giving maximum amplitude. And there are regions where they are destructively interfering, causing regions of zero amplitude called nodes. So I'm just going to outline that again, because that explanation is super, super important. So step one, you get reflection at the boundary. And as always, just drop the question in the chat at any time, and when I next have a sort of checkpoint, I'll answer that. So for instance, if we have waves on a string, so it's a sort of fixed end there, and you have a string in between. If I start a wave on one end, that wave will travel down to the right, and then it will reflect and travel back to the left. So that will cause two waves moving through each other that have the same frequency because they're realistically the same wave, just kind of reflected. So then the two waves superpose. And then you say three, when it's regions, when they arrive in phase, that is constructive interference, which causes a region of max amplitude, and it's called an amplitude, an antinode. And when they arrive out of phase, that is destructive interference. So out of phase equals destructive interference, which creates a node of zero amplitude. Well, can't spell. Illiterate. So that will look like this. I'm just going to do the first harmonic, and harmonics are things we're going to get into. Or rather, actually, no, I'll do the second harmonic. So the idea is that one point in time, it's going to look like, well, I did not draw that well at all, but let's say it looks something like that. At some later point in time, it's going to have flipped. Screw it. I'm just going to say it ends there. So in other words, this point A, at this point in time is there, and it has moved down to here at some later time. But this point B will still be this point B in the middle. In fact, I'll call it N because that will be a node. So the idea is that nodes are zero for all time, and antinodes, will it be saved later, sir? Yes. So as soon as I do a live stream, you'll be able to catch up on my channel. So you have your node in the middle, where the amplitude is always zero. And we have antinodes in between them, where the amplitude is always maximum. So the amplitude meaning it varies sort of in between the maximum amplitude and sort of that same displacement in the other direction. So that's what creates standing waves. You get that reflection, the two waves traveling through each other interfere, and we get these time-stable sort of variations in amplitude. So as opposed to a progressive wave, where the amplitude is always constant for every point, no matter what point in the wave, it will have the same amplitude. In a standing wave, the amplitude varies. So if I were to pick this point here, the amplitude is quite small. It only displaces a small amount in the positive and negative direction, whereas in the middle, the amplitude is quite big. At an antinode, the amplitude is a maximum. You get these bigger variations in displacement. So the amplitude varies along a progressive wave. Another thing is that these do not transmit. They don't carry energy. They don't propagate energy, something like that. The way they don't sort of travel in that sense. They only store energy. And also, really importantly about standing waves is about phase difference. So on a progressive wave, we know that these points are just at different points in their cycle. So this point here and this point here are a quarter wave apart. And so if one wave is 360 degrees, we consider these to be 90 degrees out of phase. So we have a progressive wave. These would be 90 degrees out of phase. So the phase varies along a progressive wave, whereas for a stationary wave, the phase works a little bit differently. So the phase can just be considered at what point in your cycle are you? Are you at the same point in your cycle? Are you at different points in your cycle? So these points on the progressive wave are at different points of the cycle. This one is sort of at the equilibrium position. This one is at maximum amplitude and about to start moving down. So they're just at different places. Whereas here, in the standing wave I have on the left, all of these points are actually at exactly the same point in their cycle between two nodes. At this point, all of the points are at their maximum displacement and are about to move downwards. And here, all of the points are at their minimum displacement and are about to move upwards. So all of these points between two nodes are in phase with each other, and they are completely out of phase with every point on the opposite side of a node. So all of these points here are at minimum displacement and are about to move upwards. So they're all in phase with each other and all out of phase with all the points on the other side of a node. So this kind of defines what a standing wave is. It has the nodes and the antinodes, and you can consider how they're set up, and you can consider their phase difference. The next thing we need to consider is how the wavelength and the frequency come about for different harmonics. So for harmonics, we're talking about the fact that different standing waves can be set up between the ends with different boundary conditions. So I will outline the three boundary conditions. So there's a closed boundary condition. No, illiterate. Try it again. It's all right. At least I'm good at talking. At least I can claim to be good at talking. Writing, tech, no. Talking, yes. So closed boundary condition. This is when, for instance, the string that we just saw, where there's a fixed, or it could be fixed. There's a bunch of different ways of sort of saying this, but these are two. Let's I'll call it fixed as well. So this one is fixed at both ends, and we can set up a number of different standing waves in between. For exactly the same length, what we know is if it is fixed, then it has to be a node. Any fixed end has to be a node. So we know the ends are fixed, which means these are both nodes, which means these are the 0 points. And we just consider what types of wave can I fit in between such that those end up being 0 points. So I can also fit in another one, which is sort of 3. Okay. And so the way to think about this is to start with the length. So we know the length between these fixed ends. Step one is to relate that to the wavelength. So here, if I were to draw a full wavelength, it would be 2L. Or rather, I often start by saying the length that I see represents half of this wavelength. Here, the length that I see represents one full wavelength. Here, the length that I see represents 3/2 wavelengths. And we can rearrange that to find what the wavelength is. So lambda equals 2L, lambda equals L, lambda equals 2/3 L. And these are the different harmonics. So this is the first harmonic, second harmonic, third harmonic. And we can see this relationship where this is equal to 2L/2, this is equal to 2L/3. So in other words, it's lambda 1/2, and this one here is lambda 1/3. And that gives us this relationship that the wavelength, in general, for any harmonic between fixed points, is going to be the first harmonic's wavelength over n. Now, similarly, for each of these harmonics, the next step, once we get the length of the string and use that to work out the wavelength, we then use the speed equation to get to the frequency. Because the idea is the speed of the wave traveling along this, in this case, string, will be fixed. And we know that v is equal to f lambda, or c equals f lambda, depending on what you want to call the speed of the wave. So if v is equal to f lambda, then frequency is the speed over that wavelength. And for each of these three cases, we can work out what that frequency is going to be. So here for the first harmonic, the first frequency is going to be v over 2L, which is lambda 1, v over L, and here f3 is equal to v over 2/3 L, which is equal to 3v/2L, which is equal to 3f1. So let me just zoom out a touch just so that you can see. And so this is equal to 2f1. And then we get this idea that, okay, in general, the general frequency for a general harmonic is going to be f1 times that harmonic. So the second harmonic is double the frequency. The third harmonic is triple the frequency. And that is where these relationships come from when it comes to these standing waves. So again, just walking through this, you start by the length, you relate that to the wavelength, and then through v equals f lambda, you relate that to the frequency. We could also have an open case, as is the case with a pipe that is open at both ends. So if we had that situation, I'll draw out the first three for you. This is probably not the clearest, but here, so if it's an open end, so I'll make a note of that here. So open, when you have open, that is antinode at both ends. So wherever it's open, you get an antinode. So the first way to do that has an antinode here and an antinode here. Antinodes have maximum amplitude. The simplest version is this, where there's the node in the middle. The next one is to introduce one extra lot of a node and antinode. So antinode, antinode, antinode. So it'll go down there and up there. And the third one will introduce, again, another node and antinode pair. And so you'll have, instead of having 3 antinodes, you'll have 4. So 1, 2, 3, 1, 2, 3, 4. So it'll start there and end there. 1, 2, 3, 4. Nailed it. It can sometimes be hard to like coordinate. And you also, like, let's be honest, we're not here because we draw well. And so we just do our honest little best, so that's fine. But here, we can again go through the process of relating the length to the wavelength. So here the length of the pipe is, so it goes from max to min. That's half a wavelength before it comes back to its starting position. So that's lambda over 2. Here, L is equal to a full wavelength. And here, L is equal to 3 over 2 lambda. So we end up getting actually exactly the same situation as we got for the close case. And I won't redo this, but we go through exactly the same process where we make wavelength the subject of the formula, and then go through V equals F lambda to work out their frequencies. And we get these exact same relationships between the wavelength of a given harmonic and the fundamental wavelength, or the frequency of a given harmonic and the fundamental frequency. The weird one that you have to be very careful of is the open-closed case. And the reason why we are about to see. So let's say we had a pipe that was closed at one end and open at another. We know of any closed end is going to have a node, any open end is going to have an antinode. So the simplest way of doing that is very simply this. Where again, we go through, we relate the length of the pipe, only this time, we say it's gone from equilibrium to max. It then has to go back to equilibrium, down to min, and then back up again. So this is a quarter of the way through, and that is a quarter lambda. The next harmonic, again, introduces one extra node, one extra antinode. So it's got to have, so it's going to be something like, it's going to have a node, and then it comes down to here. So that is the next available one. Let's see what's happening here. So that's lambda 1. So for this lambda, L is equal to, well, that's 3/4 of lambda. But you'll notice, therefore, that here, if lambda 1 is equal to 4L, whatever this lambda is equal to 4/3 L. And so what that means is this is actually the third harmonic, and that is the next available harmonic. It is impossible to get these even harmonics on an open-closed system, which is such a trap if this ever comes up for you. And the final thing to talk about is, so this is one where what we're doing is we're keeping the situation, we're keeping L fixed, and we're varying the frequency or wavelength of the wave we're putting into it, and seeing which frequencies will give us harmonics. There is another question type that a lot of people, myself included, can find very confusing, where instead of keeping the length fixed and varying the frequency you put in, it is sometimes possible to keep the frequency of the wave you put in fixed and vary the length by using water. So you sometimes see this as like this thing fills with water, or the pipe is being placed into water. But the idea here is if we have a pipe with some water in it, the water is going to change L. And so what's going to happen here? Let me demonstrate this, because I think this is the really important one. And this is the one I don't think is taught super, super well. But let's say we had some frequency of sound going into this pipe, which is fixed at one end and open at the other. So we know this will be a node. We know this will be an antinode. Let's say we set it up so it's kind of doing this. So for whatever this harmonic is. Okay. What's going to happen here is if the water level rises, in fact, I can do even better, because No, okay, I will explain this next. So what we do then is we fill it with water, and at certain points of water height, we will again get these harmonics formed. The harmonics will not be different in that the frequency will not be different, but what's going to happen is that is the wavelength. When the wave is set up such that the water level corresponds with a node, then a new wave can be set up. So in this case, when the water level reaches this level, which corresponds with this node in open space, then we can set up this standing wave. I've probably not drawn this super well, but hey, whatever. Oh, I've drawn that so badly. So badly. Let's try that again. Okay. Drawing is my downfall. Okay, then we can get this. And so what they can tell you, for instance, is, oh, the water level is set up so that, like, if this was, I've seen a question, I think that was like 33 centimeters or millimeters or whatever. Let's call it centimeters. So if that was 33 centimeters and this was 55 centimeters, that would tell you that this half wavelength is equal to 22 centimeters, which tells you that the wavelength is 44 centimeters. And so you can work out the sort of frequency of the sound that's going in to make this happen. So you're varying the water level, and that's creating nodes and antinodes that do not vary in frequency, but it's sort of the number of nodes and antinodes you can physically fit in the space. When it sort of perfectly lines up, then the standing wave forms. So this is your sort of trickier version, I believe, of standing waves. So I'm going to move on now to the optics side. If you guys have any other questions about standing waves, speak now or forever hold your peace. And I'm going to move on to the optics. So where are we with optics? From GCSE, you guys remember that there is a refractive index, which is a measure of the ratio of the speed of light in a vacuum with the speed of light in the medium. You guys also know that refraction is the bending of a beam of light at the boundary between two mediums because it changes speed. If it's traveling, if one of the mediums is more dense and one is less dense, then it means the speed will be different in the two materials, which means that changing at the boundary between the two substances, between the two media, there will be a change in speed, which causes a change in direction. That is refractive index. That is refraction. So we only really add a little bit more to that when you get into the A-level syllabus. You add onto that, well, a lot of it is recap. A lot of it is reminding yourself that N is equal to C over V, where C is the speed of light in a vacuum and V is the speed of light in a material. So in other words, the denser a medium means that it slows the light down more, which means the refractive index is higher. The version you know from GCSE is probably something like N equals sine I over sine R. I hate it. We should be thinking of this as Snell's law, where Snell's law tells us that N1 sine theta 1 equals N2 sine theta 2, and this is the A-level form. The form from GCSE, that N equals sine I over sine R, is only appropriate going from air into a medium like glass or water. Whereas this Snell's law gives us a generalized form that can cover the transitions between any two media. So this would be good for water into glass or glass into air. And so I just much prefer this. There is a derivation for this. I will cover it. I did do it in a different stream, which means I actually remember how it goes, which is very helpful. But the idea here is if we have a boundary where this is one wavefront, and this would be the sort of same wavefront. So what's going to happen here? Let me draw a little bit less of it. Let's draw a wavefront sort of that far. Perpendicular to that, this ray would kind of go to here. And if at this point, hold on, and if it bends back, so let's consider these 2 points on the wave. So this would be, for instance, A and B. At some time later, they would travel to here, which we will call A dash, and here, which we will call B dash. So the derivation of Snell's law says, first of all, this line here would be the ray. So this would be the angle θ1 between the ray and the normal. So this angle in here would be 90 minus θ1, which means this angle here is θ1. We can also then say that this ray here, perpendicular to the normal, this in here would be θ2. This angle in here would be 90 minus θ2, which means this angle here is θ2. Now we can say that we have two right-angled triangles with the same hypotenuse. So the hypotenuse is equal to AB dash. And we can say that sine of θ1 is the opposite, which is the v1 times the time interval. So that's the speed of light in this medium over the hypotenuse AB dash. And we can say that sine θ2 is equal to this opposite, which is the speed of light in that material times whatever time interval there is, all over the same hypotenuse. So what that means is that sine θ1 over v1 is equal to t over AB dash, but that is also equal to sine θ2 all over v2. And then remembering that the refractive index is the speed of light in a vacuum over the speed of light in a material, it means that n over c is equal to 1 over v. So in other words, this becomes n1 over c sine θ1 equals, from here, 1 over v2 is n2 over c sine θ2, and then the c's cancel. And you get Snell's law. Rare question, not an impossible question, because it is covered in textbook, so it is technically examinable. So that tells us refractive index and Snell's law giving us refraction. I'm also going to assume as a prerequisite that you remember total internal reflection from GCSE. So total internal reflection is when all of the light is reflected inside the medium. This happens when you're going from a more dense material to a less dense material, because in that case, it would be bending away from the normal, because the ray is always closer to the normal in the denser medium. So when you're going from more dense to less dense, you're going from closer to the normal to more away from the normal. The light bends away from the normal. There is a limit to how much that can be done, because eventually that second angle, that θ2, hits 90 degrees and cannot go any further. If you attempt to go any further, it can't, and it reflects instead. This is depicted in a sort of with 3 different diagrams. So if we have diagram 1 where it's nice and shallow, it bends away from the normal, going from more dense to less dense. Eventually, if you take it too far, that θ2 would be 90 degrees. And then this would be the critical angle. And then if we go beyond that, then it totally internally reflects because it cannot refract anymore. And that's when this is the more dense one going into the less dense one. And in this case, we can use Snell's law here to understand what's happening. N1 sine of the critical angle equals N2 times sine 90. A harmonic is an overtone. Or rather, hold on, I'll finish this off and then I'll come back and answer that common question. Remembering that sine 90 is 1, that just becomes N2. So sine of the critical angle is just N2 over N1. Now, the version you used at GCSE was that it was 1 over N because you were assuming it goes into air, but you now no longer need to make that assumption. So that covers total internal reflection. And then the uses of total internal reflection, again, a little bit from GCSE. We have these optical fibers, which are used in endoscopes, or they're used to communicate signals. So it's optical fiber. Yeah, those are the two. So one for communications, one for endoscopes, so being able to see things. The one extra bit for A level is this idea of dispersion. And then I'll come back and answer the comment question. So the idea of dispersion is that you are sending a pulse into this optical fiber, which has a fixed width, say. What's going to happen is if some of the light can travel straight through the middle of this optical wire, it's going to get to the end in less time than if something goes bouncing around like a sort of bowling ball when you have the bumpers on. So this one that's bouncing around has to travel more distance to get to the end of the optical fiber. And because time is equal to distance over speed, it means it also takes more time. So some of the light takes more time. So a pulse that went in with this thickness comes out with this thickness. So you get this spreading out. Don't worry, I'm going to reply. What I'm covering here is waves. So I'm currently on, I've just done total internal reflection. Now we're talking about the applications of total internal reflection. So we can get this idea of dispersion where a pulse of light that was very thin has spread out because some of the light takes longer to get to the end than other light within the same pulse. And this spreading out is called dispersion. And this can be a problem if you are sending pulses of light through an optical fiber that start to smear into each other. Okay, so in other words, if we send two pulses in like this, and then they spread out and overlap, then the signal would interfere and we couldn't distinguish between the two anymore, and it would just break the optical fiber. So what you can do is keep the optical fiber very thin, and that reduces that dispersion and keeps your signals nice and distinct. Common question. So the purpose of this is for the A-level exams that are happening in a few weeks' time, talking about sort of, waves, all that kind of stuff. Now, we had a common question from earlier asking, I often get confused between what a harmonic is and what an overtone is. Can you quickly go over these two? So I would say I would think of them as being the same, personally. Although I know that sometimes when you're using the word overtone, it has a slightly different connotation where it's more about these different harmonics being present in the same waveform. So as I'm speaking now, my voice has a certain note to it, but there will be certain overtones contained within that note that my voice is producing. I'm not producing a perfect sine wave. There will be overtones in that. I think that's in terms of just your physics understanding. But in terms of you actually sitting this exam, they're the same. In terms of your exam, a harmonic is an overtone, and that should be fine. Although harmonic is the simple version. So yes, just letting you know if someone's new to the chat. So I'm a professional tutor. I do live solves of math papers once a week, and I do a once weekly physics live seminar, which you've stumbled across now, where we're going through the stuff almost like a tutoring session, the way you would sort of preparing for exam. This is aimed at students who are sitting their A-levels in a few weeks' time. And it's also for people who seem to like to sort of tune in and listen to the cadence of my voice as I talk, because apparently I'm weirdly calming as I guide people through into their A-levels. So yeah, that's me. That's what I'm about. Now, if you want to stick around, you are be treated to interference, which is the last thing I want to talk about. So the idea here is let's talk about, first of all, double slit experiment. So with the double slit experiment, we have light from the two slits arriving at a screen. Because the light has traveled different path lengths to get to the same point, there is a phase, there's a path difference of the two beams, and therefore there's a phase difference of the two beams. Actually, before we get into this, very interesting common question. What's the difference between voltage and EMF? Basically, if you think about, I'll get more into this when I do the circuits stream that I'm planning on doing, but you can consider current to be like a fleet of Amazon delivery trucks. So at the sort of warehouse, they pick up all the packages, and then they go off into the road and they distribute the packages. So they're picking up the packages at the warehouse and they're distributing them at the houses. In this analogy, the warehouse would be the battery and the houses would be the resistor. Typically, when we're talking about voltage, we talk about decreasing that potential. We talk about getting rid of the packages. So this tends to happen at the resistors or the houses. EMF is more about the battery. That's where you pick up the packages. That's where you're gaining potential. So EMF is like the driving force where the potential goes up and it's given all of its potential. And voltage tends to be the drop when it goes through a resistor. You are the first person to tell me I look like Jake Gyllenhaal. Congratulations, sir. I get Daniel Radcliffe all the time. I also have, when I'm wearing my glasses, nerdy Tobey Maguire at the start of the Spider-Man movie. I just look like every generic white actor. But thank you very much for saying I'm in that league. I will take it. So, getting back to the whiteboard. Let's get into this. So the idea is we have these two different waves from different sources meeting at a point. Because we have two waves meeting at a point, they will interfere. They will have that same superposition we talked about earlier. Because those two waves travel different distances to get to the same point, there is a path difference. That path difference introduces a phase difference. When the two waves arrive in phase, they will have constructive interference, which leads to maximum amplitude and a bright fringe. When the two waves arrive out of phase, there will be destructive interference, causing a dark fringe. So here, if I draw this line here, this shows the path difference. I know this is a little bit sort of different because it's not sort of great, but in terms of the diagram, but this would be the path difference. The light from the second, the lower slit, has to travel a further distance to get to the same point. So there's a path difference in the two beams, and that path difference causes a phase difference. Now, showing you what happens here, those two beams, if we draw them as roughly parallel, where these would be the two slits, right? So slit 1, slit 2. This is creating two parallel beams. So I can even draw like the waves on, right? If they are constructively interfering like this, if they are like completely locked up with each other, this happens when You have one complete wave up until that point. Now they're in phase with each other. Boom, good to go. You get that maximum constructive interference. So when the path difference equals n lambda, that's when you get constructive interference. And we can do a little bit better here. So we can say that there is this angle to the screen. And it may be hard to convince you of that, but the angle to the screen would be the same. Nope. Shouldn't let me touch things. How do I? Cool. The angle to the screen is the same. Well, because these are technically in parallel with each other, but the angle to the screen, that theta there, is the same as this angle in here because this meets at right angles. And so what we can say is this distance between the slits, which I will call S, which is the hypotenuse of that right angle triangle, I can say that sine theta equals the path difference over S. So the path difference equals S sine theta. I can also say from this big diagram that is the distance up there, and this is the distance to the screen D. So for the first instance of a maximum intensity fringe, so when n is equal to 1, when the path difference is lambda, this would be little d, which is the distance between fringes. So we have a central bright fringe and then a next bright fringe, and the distance between those will be the fringe separation when n equals 1. So when n equals 1, you would get the path difference is equal to lambda, and we would say that sine theta is equal to lambda over s, but sine theta would also equal, from this macro image, little d over big D. Assuming small angle? Maybe that is assuming small angle. Maybe I'm getting this derivation wrong. I'm just going to stop saying things, but I will say that I know the derivation is right for diffraction gratings. Hello. So what we have here is you end up finding the slit separation is lambda d over s. No, am I getting this totally wrong? Hold on. Textbook, sorry, going off the top of my head, and it is not working. Why is this not working? Yeah, lambda d over lambda big D. So depending on how you define these things, I've seen this for the IB, where this is I've seen width is equal to lambda d over s. Apologies for that slight brain fart. But the idea here is that these are the fringe spacing. And little d or s is equal to the slit separation. What was I missing about that? How to master physics, how to become stronger in physics. My idea for that is to dig deep and keep asking why. So for instance, don't just take it when someone gives you an equation, think why it makes sense. Can you draw this diagram and understand why the path difference has to be a whole number of wavelengths to get constructive interference? Can you kind of imagine what would happen if that shifted a little bit? So dig deep and keep asking why, and never move off it until you're satisfied that it really holds. So yeah, basically why all the way down. That is how to master physics. So the example I give people is, for instance, when you're jumping out of a plane and you're reaching terminal velocity. Okay, you might say, oh yeah, terminal. Actually, I'm answering comment questions. I should always stop sharing screen. You are very, very welcome. So for instance, terminal velocity. You think, okay, it reaches terminal velocity when the weight equals the drag. Okay, cool, but why? Okay, so then those forces are equal, which means there's no resultant force. And by Newton's first law, when there's no net force, it will move at constant velocity. Ah, so it comes from Newton's first law. Okay, but how did it get there? So you jump out of a plane and you're accelerating downwards. Okay, but why? Because you have weight acting downwards, no force acting upwards. That's causing a resultant force downwards. And Newton's second law tells us that when there's a resultant force, you get an acceleration. So that means it's accelerating downwards. And then as the speed is increasing, the drag is increasing. And then that is decreasing the resultant force, which decreases the acceleration until, bingo, they're equal. So keep digging down and don't move off until you're very satisfied that you can do this, therefore this, therefore this, therefore this, and walk yourself from one end to the other, hitting every important point on the way. That is how to do well at physics. So getting into here, two triangles are very similar in shape. Do I want to... Yeah, so it kind of comes from that. So it was the lambda. I'll give it one more go. So it does come from the idea that I think that in this case, that lambda over s equals d over d. And so you can rearrange it and say that lambda d over d is equal to s in this form, depending on how you're defining your terms. So it does come from these two triangles, right? The one relating path difference with the slit separation and the one relating the fringe separation with the distance to the screen. So that is double slit. I want to point out quickly that single slit diffraction also happens. But the only thing I really want to go over here is that the central fringe is twice as wide as all the other ones, and then you get this massive drop-off. So if that is fringe separation W, then that is also W, so the central maximum is sort of 2W, which is why the central maximum is 2 lambda d over A, where A is the width of the single slit. Now, the final thing I want to go over today is the diffraction grating. With the diffraction grating, we have a number of lines on the diffraction grating. So if there are n lines per meter, then it means the distance between each line is 1 over n. So distance between the lines. When we have, in fact, I feel like I went through this recently, and I'm worried I'm going through something I've already gone through. But this might have been a common question. I think it was, or might have been a different context. How can one get rich with a Natsky degree? Many options here. In fact, common question, let's go through that. You can get rich with a Natsky degree by going into finance directly, because you show you have numeracy skills. So I actually did used to work for a big bank. You can get rich by becoming a patent attorney. You can start a business. You can not go into academia, I'll tell you that much. It depends on what you define as rich, I suppose. Because you can get certainly some very high salaried jobs that are very technical. So you can get very high salaried jobs in engineering, electrical engineering, these sorts of things. Yeah, you can go to a lot of places. How much are we talking? Depends on the industry and what you're going to do. In the UK, also consulting. A lot of consultants come from there. So patent attorneys, like you can easily get. How long would it take you to get over 100K? You can easily get over 100K with a Natsky degree if you want to. I mean, like if you go into quant trading, you can hit over 1 million by the. Like I actually know of someone whose younger brother was hitting 1 million by the time he was 25, but that's because he sold his soul to do like quant algo trading stuff. and that's like his entire life. I think sort of normies, you can be hitting 100K by the time you're 30 if you want to. Which one is more enjoyable? I mean, that's up to you. I don't know what you find enjoyable. That is entirely up to you. But you work this out as you go along, right? You work out what you like, what you don't like, what you can sustain, what you can't sustain. So I worked out very quickly that I just can't psychologically sustain work in a corporation. I like doing this. I like being able to use my full personality, be self-employed, go chasing the work where I can. This works really well for my personality type. And that really matters. It's not just sort of going, where's the money? Just blindly do that. Work yourself out. Solve the problem of yourself, what skills you have, what you don't, what you can sustain, what you can't. Assemble that into a career path and you'll be fine. Because I was technically on paths that could have earned more money, but I was not the sort of person who could do the things I needed to do to go get that money. I got my money by getting out of those places and doing my own thing. So but you've got ages to work all that out. Coming back quickly here, because I've got to dash quickly. So we've now worked out the distance between the lines of a diffraction grating as being 1 over n, where n is the number of lines per meter, which means that the distance between all of these slits is d. And because we have so many slits, if we go off angle just a tiny bit, even if it was something like, 1 degree off, then let's say the path difference between each of them was just like lambda over 100, right? If you go 50 lines down, that's 50 lambda over 100, which is lambda over 2, which is perfectly out of phase, and you get destructive interference. So what we find is not sort of diffraction, sort of fringes where they have any width to them. It's beams. Only extremely specific beams are allowed, where the path difference is equal to n lambda. So every single one of these parallel beams is perfectly in phase. So this happens when the path difference is perfectly equal to n lambda. And as we saw before, the path sine of the theta is equal to the path difference over this separation of the lines. So it's n lambda over d. And so n lambda equals d sine theta. And if you shine a beam of light at a diffraction grating, you will see it split out into these different beams of different orders. So I haven't drawn this exceptionally well, but this would be n equals 1 beam, n equals 2 beam, n equals 0 beam. And again, you get an n equals 1 on the other side and n equals 2. And so what you can also do with this equation, the n lambda equals d sine theta, is you get like the maximum order fringe that you can get, because the biggest that theta can get is obviously 90. So n max would be equal to d over lambda when sine theta is equal to 1. So this would give you the maximum order of the beam that you would be able to see. And I think that is a very good place to leave wave and optics. You are very welcome. So what I'm planning next is I know I need to go through simple harmonic motion and circular motion. I know I need to do electricity and circuits. And I know I need to do, I've done thermal, but I need to do all of the sort of forces, work, motion, energy stuff if I can. So I'll try and get as much done as I can before the AQA exams start. I know the AQA ones actually are after the half term. So all of my students have their first physics exam only after the half term, but I know some people have it earlier. So as always, feel free to A, do the YouTube-y things, but also B, if you want to join the Discord server, you can recommend topics for me to go over. Astrophysics, that's a good idea. So that's exactly what I mean. If you have suggestions you want to put in, the Discord server is where to do that, and that will inform where I put my energy in. Sort of doing as much as I can to help you guys before the exams, but I don't think I'll be able to get through every single topic. If you want to prioritize the ones that work for you, that's where you make that happen. I hate parsecs. Yeah, Astro is weird. Um, to be honest, the thing with Astro though is you kind of just memorize the life cycle of a star and you're fine. Like, there's not much for me to explain. It's more for you to memorize it. So like the evidence for the Big Bang in terms of cosmic microwave background radiation and galactic redshift. I think there was a third, but I can't remember what. Oh, yeah, those sorts of things. Yeah. So a lot of it is sort of knowledge as opposed to understanding. I think and not everyone does it. So I think my efforts are better spent on things like circular motion, forces, motion, energy, and circuits. So I'm going to start there. If I can get into some of the more niche topics, I will. But in the meantime, I'm going to keep people updated in the Discord server about when I get to go live. My schedule now is going to be super, super, super in flux as people move around. When you have exams on different days, it gets really irregular. So that's where to get the sort of updates of when I'm going to go live. I will try and populate here on YouTube with enough notice so you guys know as well in advance. And looking ahead, by the way, I think my next physics is probably going to be Tuesday in the evening around 7 p.m. So keep an eye out for that. In the meantime, have fun, keep studying, keep doing them past papers, and I'll see you next time. All right, have a good evening, guys. Take care. Bye-bye.